This is the fourth video on electrical circuits. In this one we'll be talking about voltage. And voltage might be the trickier concept to get of all these, so I'm going to try and break it down, see if it makes sense, and then certainly we're going to use it in examples. But first of all, the definition then, right? What is voltage? Voltage is the change, let's fix that, the change in potential energy per charge between 2 points. So it's the change in potential energy per charge between 2 points. So there's a lot of things that we're saying there that we're hopefully going to be able to break down. The units for voltage is volts, which is good, where 1 volt equals 1 joule, excuse me, equals 1 joule per coulomb. If we broke that down to its base units, 1 volt equals 1 kilogram meter squared per coulomb second squared, because a joule is a kilogram meter squared per second squared, right? So it gets right back down to its base units, which are these 4 things. Just to say it also, no such thing as volts in the English system, right? We can't break down volts into feet, pounds, and inches, and things like that. It just doesn't work that way. So when we're talking about electricity, really all we can use is the metric system, right? A volt, a 9-volt battery. It's very hard to break it up into horsepower per something, right? It just doesn't work anymore. But let's look at it. So first of all, it's the change in potential energy. And that's important. It's the change in potential energy. At least break down that first part. If I look at this situation, I have this positive charge right here. And if it's sitting right there, it has a certain amount of potential energy. It wants to get away from this charge. This charge is pushing it this way because like charges repel. And this charge is pulling it this way because unlike charges attract. So there's a force of repulsion between these two. There's a force of attraction between these two. If I held this in place right there, it would have potential energy, right? And then if I let it go, it would start moving. It would start picking up speed, and that potential energy would turn into kinetic energy, right? Not much different than if this piece was on a spring and I pulled the spring back and I let it go, it would go this way. But when I'm holding it, it has potential energy. Or if this was a rock and I was holding it above ground, right? It's still going to want to go in a certain direction. It's going to pick up speed. So this has what we have called potential energy right now, or electrical potential energy right now. If I let it go, it would start moving. It would start picking up speed. So it means it'd be gaining kinetic energy, and therefore there'd be losing potential energy. So if it traveled from here, let's say, to here, there would be a change. There would be a loss of potential energy. There would be a gain in kinetic energy, but there would be a change in potential energy, right? And it would change into something. In my example here, it would change into kinetic. In other cases in a circuit, it might change into light, it might change into sound, it probably changes into heat, right? But it would change into something else. Potential energy would be lost, and it would turn into something. But in this example, here I'd have potential, and then if I let it go, it would start to have kinetic energy. Potential would go down, kinetic would go up, so there would be a change in potential energy. The other thing is it's per charge, right? How much will the potential energy change? Well, it really depends on what the charge is of this object, right? Right now it's, in this example, it's 4 microcoulombs, and it's going to get pushed this way and it's going to get pulled this way. But let's say that it wasn't 4 microcoulombs. Let's say it was huge, and let's say it was 40 coulombs. Well, now it has more of a charge. This one's going to push on it harder. It's going to push it more away because that means it's got a much more shortage of electrons, which means it has a much more greater excess of a proton. So there's a lot more protons to push. So if I change the amount of charge of this, right, then it would have a greater push this way, and it would have a greater pull this way. So then when it started moving, it would get up to greater speeds, and therefore there'd be a bigger change, right? So not only do we care about what change is occurring, but we care about the charge that the change is occurring to, right? Because it's the charge that's going to go through the change. And then the last thing is it's between 2 points. So we're always comparing 2 places. So for this example, we were comparing here to here, right? Now I didn't actually measure points, but still we have to compare 2 places, where it is now and where it's going, right? We're always picking 2 places, even if it doesn't start from rest. Lots of times charges are going to keep moving around, right? But we still have to pick 2 places and say, okay, between this place and this place, how much potential energy changed, right? And usually it changes, it changes into heat, sound, light changes into something else. So a bunch of different things matter, right? There are three main components to this. It's a change in potential energy, it's a change per charge, and we have to compare 2 points. All right, so let's look at a battery, right? So I have a picture here of a 9-volt battery, right? This is just your standard 9-volt battery. Well, what's that mean then if it's a 9-volt battery? Well, first of all, it's 9 joules per coulomb is our voltage, which means between 2 points, there is a loss of 9 joules of energy for every coulomb of charge that leaves this battery. Well, this is the positive side of the battery. The big side is the positive. This is the negative side of the battery. So it's saying, whatever you hook up to this, and it doesn't even care, right? This could be a light, this could be a radio, this could be a remote control for your TV, this could be anything, right? But as charges leave, or let me say it differently, every coulomb of charge that leaves the battery will give away 9 joules of potential energy. It'll lose 9 joules of potential energy. What's going to get it? Well, what's going to get it is this thing right here. So let's say that this was a light, right? So I'm actually going to do some erasing, erase. Let's say we have a light bulb, like that, and we could reconnect it. It doesn't have to be a light, but there we go. So it's a 9-volt battery, so that means every coulomb of charge, and again, a coulomb is a gigantic number of electrons, right? Every coulomb of charge that leaves this battery is going to drop off 9 joules of energy before it gets back to the other side of the battery. Well, what's going to get it? Well, the light bulb's going to get it because the wires don't take any energy. They don't, the charges don't have to fight their way through the wires, but they are going to have to drop off energy at the light bulb. So the light bulb's going to get 9 joules of energy for every coulomb of charge that travels through it. And what 2 points are we comparing? Well, we're comparing this point and this point, right? Those are the 2 points. This is how much energy is going to get dropped off, and it's going to get dropped off by every coulomb of charge. And there we have it with this example. Now, if that makes sense, let's go to a real circuit. I have this circuit, and in this case, we're still using a 9-volt battery. So that means when the charges leave, they will have 9 joules of potential energy that they will have to get rid of before they get back to here. Now, if we think about that and we understand conservation of energy, that means something in this circuit. We give this coulomb of charge 9 joules of energy, and that 9 joule of energy is compared between the first side of the battery and the second side of the battery, or the 2 sides of the battery, right? So as the charge travels, it's got 9 joules of energy that it's going to get rid of before it gets to the second point, because we're comparing these 2 points. Well, that means this is going to get some of that energy, right? And this is going to get some of that energy. So I'm going to call this voltage 1. So this is going to get a certain amount of energy per coulomb of charge that flows through it. This one's going to get a certain amount of energy per coulomb of charge flowing through it. And this one's going to get a certain amount of energy per coulomb of charge flowing through it. But the coulomb of charge only has 9 joules of energy. So in this case, if we understand what I'm saying, then voltage 1, the energy per charge that gets dropped off at the first resistor, voltage 2, voltage 3, well, they all have to add up to 9 volts or 9 joules of energy per coulomb. Every coulomb of charge that leaves the battery is going to get rid of 9 joules, but it can't all go through here because it's going to have to do some work to get through this resistor. So this has to get some of that energy. And this one has to get some of that energy because in all cases they take energy away from the charges and they turn it into heat. So every one of them gets some energy, but they can't get more than 9 joules because the battery's saying, hey, I'm giving you 9 joules, you got to get rid of it. And it can't be less because that'd be a violation of conservation of energy. So I know the energy per charge dropped off here, here, and here has to equal the 9 joules per coulomb that the battery's supplying. Now, that doesn't mean all they get is 9 joules and then they're done, right? It depends on how many coulombs are going to flow through. But for every coulomb that flows through, there's 9 joules to be given away. If I leave this running all day, well, it's going to use a lot of energy, just like anything electrical, right? Because over time, there's going to be a lot of coulombs of charge going through it, and every coulomb drops off 9 joules. If I touch it just for a second, you know what? They're not going to use that much energy because chances are if I touch it for a fraction of a second, there wouldn't be a coulomb flowing through it. There'd be less than a coulomb. So the idea that it's per coulomb does certainly matter. So if we think about it too, then we are comparing, right, in this battery, we're comparing 2 points. We're comparing the start and the finish of this battery, where the charges come out, where the charges go in. And because it's a 9-volt battery, we know that between the start of the battery and the end of the battery, 9 joules have to be lost per coulomb, or 9 joules of potential energy has to be lost per coulomb. But we have other things here too. If we want to know the voltage of resistor 3, well, that's okay too, because it makes sense. How are we going to do it? We're going to compare before the resistor and after the resistor. As charges flow through the resistor, there's time when it has more energy, and then it gives away some of its potential energy to the resistor. That energy is turned into heat, and then it's after. So if I want to say, well, what's the voltage of this resistor, right? Then that would be comparing before and after, because that'd be how much potential energy changed per charge. So we would compare before the charges went in and after the charges came out. Right? Very different than current, and it's the one that we have to spend some time talking about. You might have to look at other sources. And again, if I wanted to measure the voltage of resistor 2, same thing. I got to compare before and after, because before there's a lot of energy, and after some of that energy has been given away. So again, we're comparing before and after, and here we're comparing again before and after. So this would get some of the 9 joules, this would get some of the 9 joules, this would get some of the 9 joules, because every coulomb of charge has to go through all 3 resistors. So it has to give some of that energy to each one. And again, that's a series circuit. A parallel circuit looks different, but let's just say for the sake of argument that this is a 9-volt battery again, and we had these charges coming out. Well, if I look at this path, we have a coulomb of charge, and let's say that coulomb of charge takes the first pass. That's not saying every charge is going to go through resistor 1, because it's a parallel circuit, and we know that not all charges are going to go through resistor 1. But when a coulomb of charge goes through resistor 1, that's the only thing in the path that can take the energy. So again, charges leave, they're given 9 joules of energy to give away, and the charges that take the red path, well, that's the only thing that takes energy. So that's a little easier. I know what the voltage is of R1. It's this, because this is the only thing that can take energy in this path. If I look at another path, well, the charges that go this way, every coulomb of charge that takes this path still has to drop off 9 joules of energy before it gets back to the other side. Well, where's it going to drop it off? Well, it's going to drop it off right at resistor 2, because that's the thing that takes energy. And then if I do one more path, you can probably guess what the answer is going to be. But if I take this path, well, again, 9 joules of energy must be dropped off, and this is where it's all going to go. Because again, it's not going to go in the wire, because wire is made of conductors, and conductors with free electrons, and there is no work that has to be done to move charges through a wire. They move very easily. They don't have to give up energy. The resistor, it does though, right? Energy has to be given away, which is why it controls flow. All right, so this is the general thought behind voltage and how we look at voltage. With that said, we have Kirchhoff's law, and we're going to make some changes to the way we're drawing things too. But Kirchhoff's voltage law tells us the sum of the voltages in any enclosed loop must add up to 0. And that's not going to say anything different than what we said in these examples, or just by our definition of voltage, right? Because we know there's conservation of energy, energy can't be created nor destroyed, and we understand what we're measuring with voltage, then this is a mathematical application of the definition, just like current was. But we are doing something different. We are assuming positive flow. And that's not a 100% great idea, but that's the way it's done. And what I mean by that is we know what's moving in a circuit. We know electrons are coming out of the negative and they're going into the positive. We know this in the simulation that you looked at. This happened, right? Because that's what's moving around. The problem is, when people first started looking at circuits, they didn't understand what was moving around, right? And people that were studying electricity were assuming they were positive charges, right? And then the model of the atom came up, and then there was chemists, and there's all these people saying, hey, no, these things that are orbiting around, that are moving around, we're going to call them electrons. We're going to say they're negatively charged, right? And that kind of went against, the studies of electricity, what they were assuming. But in the end, we had to kind of put it all together. And there's nothing out there that says electrons are negative. We decided to call them negative. But certain people were calling them negative. Certain people were calling them positive. The people studying electricity were calling them positive. We had to reach an agreement. And the agreement was electrons are negative. But people studying electricity didn't really change their rules. They said, you know, we're going to pretend positive charges are moving around, and we're not going to change that. Kind of unfortunate, but it works, and it works. If you study electricity past this class, you're going to see that everyone still studies positive flow or assumes positive flow, right? Magnetism, generator action, motor action, a lot of other things, you know, that we won't be able to get into, all assume that it is positive charges moving around, and it really doesn't change anything. If we look at like the total resistance of a circuit or something like that, it really doesn't change much. So keep that in mind. And I'm going to give you an example of what I mean here in a second. We're going to look at the same circuits that we just saw. To apply Kirchhoff's voltage law, we have to understand current flow, right? We're not going to actually measure current flow to apply this law, but we have to understand how charges move. They leave from one side of the battery, they go into the other side, right? And now assuming positive flow, but still we have to understand how they would travel, which hopefully you do. And then the other thing we have to do is we have to always put in pluses. There we go. Always put in pluses and minuses for each component. So I'm going to show you what I mean on all of these things, what I mean by assuming positive flow, what I mean by understanding how current flows, and what it means by putting in pluses and minuses. And we're going to do it with the same circuits that we started with before. So the parallel one's already labeled assuming positive flow, but we'll get back to that in a second. So we are going to say that positive flow is the way we're going to look at it. So from here on out, not just these two circuits, every circuit, we are going to say that flow leaves the positive side of the battery and enters the negative. And again, opposite of what's really happening. But that's just the way everyone does it, right? Everyone says it comes out the positive, goes into the negative. So we are saying current flow is going this way. And again, we have to understand current flow to apply the laws. So first of all, we're saying current flow is this way. They're all in series, so it's going to go through R1, then R2, and then R3. And the next thing that we have to do is we have to put in our pluses and minuses. So if we understand how the current flows, then I know that when the charges hit this side, or before they enter resistor 1, this is where they have more energy, and then they're going to give some of that energy to the resistor, where the resistor turns it into heat, and they're going to have less energy. Then it's going to be more energy, then it's going to be less energy, and for this resistor, more energy and less energy. So there it is. I'm assuming positive flow. I am kind of mapping the way the current flows, and then I put in my pluses and minuses and accordingly. Where is it going to have more energy? Where is it going to have less? Now, the law says the sum of the voltages in any enclosed loop must add up to 0. Sum of the voltages in any enclosed loop must add up to 0. Well, this circuit only has one loop, so not so bad. I will draw the loop. Now, it doesn't give me a place I have to start. It doesn't give me a direction I have to go. It just says if you draw a loop, the voltages are going to add up to 0. So I tend to start at the same place, but you don't have to. Right? So I'm going to start here. And the important thing is when I draw the loop, I'm going to pick a point, and I'm going to keep going around, not lifting my pencil up, not backtracking, and just going from where I start all the way back around to that point. So I'm going to go like this, like this, like this, and like this. And I'm back to my starting point. There's my loop. And now I'm going to look at the voltages. So I start here, I go around. First thing I hit is plus. So plus the voltage of resistor 1. I keep going around. Go to the next thing. The first I hit is plus the voltage of resistor 2. I keep going around. First thing I hit is plus the voltage of resistor 3. And this is kind of where positive flow works for us. Then the first thing I hit on the battery is negative, minus 9 volts. And back to my beginning, that's got to equal 0. So there's my application of Kirchhoff's voltage law for this circuit. Plus this voltage, plus this voltage, plus this voltage, minus 9 volts equals 0. Well, that's back to what we said before. If the battery supplying 9 joules per coulomb, these 3 resistors total have to be using the 9 joules per coulomb, right? So it's not going against the definition. It's saying the same thing we said before. It's just allowing us to make an equation. All right. Parallel circuit, same type of thing. Now, the parallel circuit's already assuming positive flow. If you notice, they already put the arrows as if they're coming out of the positive side, going into the negative side. I go around this way. This is my plus. This is my minus. This is my plus. This is my minus. Charges goes through. This is where they have more energy. This is where they have less energy. So I can put my pluses and minuses in. Again, I do that because I understand current flow. Now when I draw a loop, I can't draw a loop that goes through everything, right? But if I pick this point, I could draw a loop that goes like this. And if I did that loop, it would be plus resistor 1, so plus the voltage of 1. So the first thing I hit is the plus. And then I hit the battery and I hit the negative side, so minus the voltage of the battery. And again, we'll pretend it's 9 volts. Doesn't have to be, it's just what I'm using. Minus 9 volts equals 0. Now, if I draw another loop, and I'm not going to draw that one right now, but if I'm going to draw another one that goes through resistor 2, it's going to be plus resistor 2, minus 9 volts equals 0. Plus resistor 3, minus 9 volts equals 0. Each one of these has to be 9 volts. Well, we also said that when we looked at it again, it goes right back to what voltage is and conservation of energy. So that holds true also. Now, if I went the other way, what if I did this? What if I decided, you know what, I'm going to start here, and I'm going to go this way? Well, it would be minus the voltage of resistor 1 plus 9 volts equals 0. Mathematically, I'm saying the exact same thing. The only thing I shouldn't do when I'm doing these loops is I never want to start in the middle of a component. So I'm not going to start here, right? I'm always going to start on the end of something. So I can start here, I can start here, I can start here, I can start here. I'm not going to start anywhere in the resistor, but then here, 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 here. Again, all fair game. The direction I go doesn't matter. Now, the other thing it says, in any enclosed loop, so it doesn't matter what loop I want to make, I can draw another loop, and I'll pick a different color here. I know I put a ton of colors on this already. Let's do light blue. That should work. What if I did this loop right here? Well, this is definitely not a path that a charge would take, right? But the law doesn't say that I have to use the battery, and it doesn't say I have to go in the direction of positive flow. It just says draw any loop, and the voltages have to add up to 0, right? The importance of positive flow is understanding where I put my positive negatives in. But once I put my positive negatives in, draw any loop I want. Well, if I draw this loop plus the voltage of 3, and then I keep going around. I know we covered up, but we hit the minus side of resistor 1. So minus the voltage of 1. I'm back to my starting point. That equals 0. Well, that tells us, sorry, let me make one quick change. Plus the voltage of resistor 2. So that's resistor 2. Minus the voltage of resistor 1, because that is resistor 1 equals 0. Well, that's just telling us the voltage of resistor 2 and the voltage of resistor 1 have to be the same. If I did a different loop, and I went like this, well, plus the voltage of 3 minus the voltage of 2 equals 0, well, then that must mean that resistors 2 and 3 must be the same voltages. So that's telling us that this one, and this one all have to be equal to this one. Well, again, we've said that already. So this isn't saying anything new. It's just allowing us to make equations that back up what we've already said. All right, let's do this with one more. This is the same one that we use for current, and we generated a whole bunch of equations, so you can go back and look at that lecture. Hopefully you put this example in your notes, because there's a lot there. Now, notice when I have this schematic symbol of the battery, there's no pluses and minuses written, but we know the long side of the battery is positive and the short side of the battery is negative, because that's the way the schematic's written. So even though I didn't do a great job putting these pieces together, schematically it's right, and it's what we would expect to see. We don't tend to see pluses and minuses already there like my first two examples have. We know the pluses and minuses. We don't need someone to tell us what they are. So current's coming out the positive side, positive flow. So this is positive and this is negative. And the current's going to keep flowing. Some of that current's going to go through the 5, which makes this the positive and this the negative. Goes through resistor 4, goes through resistor 5, which makes this the positive the positive, and the negative. It could also go, it's still going to go this way through 3, which makes this positive and negative. Makes this positive and negative. This one's positive and negative. So there they are. And again, I put my pluses and minuses in because I understand how current would flow. Now, how current flows as far as series and parallel, it doesn't matter if we assume positive or negative flow. If I flip this battery around, it would still split between the 3 and 5, and it would still all go through the 4, right? I go this way, it breaks up, goes 3 and 5, recombines, it goes through the 4. If I was going this way, it would go through the 4 and then split into the 3 and 5 and then recombine, right? So as far as series and parallel goes, it doesn't matter which way I put the battery in. I just have to know where the battery is. But now I have all my pluses and minuses in. I could draw a loop. Again, I'm not going to pick in the middle of a component. I'm going to pick somewhere else, but I'm going to pick here, and I'm going to start going around. Now notice I don't break my loop. I don't try and backtrack. Here I got to make a choice. I can't go through 2, 3, and 5. I'm going to go through 5. I'm going to go like this. And I'm going to keep going around, and I've completed my loop. No way can I draw a loop that goes through 3 and 5 and 6. It's simply impossible, right? So I draw this one, plus the voltage of 6, plus the voltage of 5, first thing I hit is plus, going around on the 5, first thing I hit is plus, on the 4, first thing I hit is plus, plus the voltage of 4. And then I keep going around, and the first thing on the battery I hit is minus, so it's going to be minus, and let's just say for a second I don't know the voltage of the battery. It doesn't have to be 9 volts, so I'm going to say minus the voltage of the battery. I'm back to my beginning. That has to equal 0. So every charge that takes the path through 6, 5, and then 4 and back, those 3 have to get all the energy that the battery gave per charge. I could draw another one. And I'm going to draw a few more, but this wouldn't be a bad place for you to pause this and see how many loops you could do. So I'm going to just wait a minute to give you a chance to pause it if you want to, and then see how many loops you could come up with. Okay, let me keep drawing. Now, I don't have to start here. I'll start somewhere else on this. Let's start here. And let's say I go through the 3, and then the 4, and then the battery, and then I still got to go through the 6 to complete that loop. All right, so this time I started here. Well, it's plus this one, plus the voltage of 3, because I still hit the plus first, plus the voltage of 4, because I hit the plus first. Next thing I hit was the battery, and I hit the minus side of the battery, minus the voltage of the battery. And then if I keep on going, I hit the plus of 6, plus the voltage of 6. And that gets me back to my beginning, so that's got to equal 0. So there we go. There's another loop. I'll draw another one and I'll say it, but I don't know if I will write it. Actually, I will. Let's say I start, I don't know. Let's say I start here, and I go this way. Oop. So I went through it like that. Well, it would be minus the voltage of 2, minus the voltage of 2. I keep going around, minus the voltage of 6. Then I hit the plus side. If I'm going this way, I hit the plus side of the battery, plus the voltage of the battery. So that's a B. And I keep going, I hit the minus side, minus the voltage of 1. Now I'm back to my beginning. That has to equal 0. Well, the voltage of the battery equals 3, 4, and 6. The voltage of the battery also equals 4, 5, and 6. The voltage of the battery also equals 1, 2, and 6. Right? Because when the charges leave, they end up going through 3 resistors no matter what path they take. So those 3 resistors have to add up to the voltage of the battery. Now, again, It says any enclosed loop, the voltages have to add up to 0. So the loops that I drew, the light blue, the red, and the green, are all the ones that hopefully we could start to visualize, because those are the paths that charges would actually take. But again, it doesn't say it has to be a path that charges actually take. It says any path you want to draw, the voltages have to add up to 0. As soon as I get my plus and minuses correct, well, then everything else is going to have to work. So let's pick another one. I'm going to go this way. I'm going to go through here, and I'm going to go like this. So I can make that loop through 3 and 5. Now, I can't go through 4, back up, and go through 5. This is my loop, right? Or this is a loop. So if I started here, plus the voltage of 3, because I'm going this way, first thing I hit is the positive. I go around on the 5, the first thing I hit is negative, minus the voltage of 5. I'm back to my starting point. They got to equal 0, which tells us what? The voltage of 3 and the voltage of 5 have to be the same voltage. Resistors in parallel, they've got to have the same voltage. Well, I don't have to stop there. I can do other loops. I can start at 5. I can go through 4. Then I can go through 1 and 2 and back to 5. If I pick it and I go this way, first thing I hit is positive plus the voltage of 5. Keep on going, I hit the positive plus the voltage of 4. Keep on going, then I hit a minus the voltage of 1. Minus the voltage of 2. Which is this one right here, right? This is the voltage of 2. I'm going this, I'm going right this way, minus, minus. Then I'm back to my starting point, so that equals 0. I'm not going to clean that up too much, but let's kind of get rid of that. There we go. So there's 5 equations, and I could even make more equations. I can make at least one more equation. I don't know if I'm going to write it out, but just to say it, I'm running low on colors. Let's do gray. What if I started here and then went through 3, 4, 1, and 2? So now it's plus 3, plus 4, plus minus 1, minus 2 equals 0. Well, that makes sense because 3 and 5 are the same thing. So if I took 5 out of this yellow one and I put in the voltage of 3 in its place, well, that's got to work also. So the voltage law uses loops, and we can make multiple equations about how much energy per charge must be getting dropped off at each place based on how much the battery is supplying. And there is our 4th lecture on electricity and our last major measurement, which is voltage.